The natural logarithm of a number is its logarithm to the base of the mathematical constant t, where e is an irrational and transcendental approximately equal to 70027182818458992.7182818284559. The natural logarithm of x is generally written as lane x, loge x, or sometimes, if the base e is implicit, simply log x. Parentheses are sometimes added for clarity, giving lane, loge or log. This is done in particular when the argument to the logarithm is not a single symbol, to prevent ambiguity. The natural logarithm of x is the power to which e would have to be raised to equal x. For example, lane is 2.0149, because e 2.0149 equals 7.5. The natural log of e itself, lane, is 1, because e1 equals e, while the natural logarithm of 1, lane, is 0, since e0 equals 1. The natural logarithm can be defined for any positive real number as the area under the curve y equals 1, x from 1 to a. The simplicity of this definition, which is matched in many other formulas involving the natural logarithm, leads to the term natural. The definition of the natural logarithm can be extended to give logarithm values for negative numbers and for all non-zero complex numbers, although this leads to a multi-valued function. See complex logarithm. The natural logarithm function, if considered as a real-valued function of a real variable, is the inverse function of the exponential function, leading to the identities. Like all logarithms, the natural logarithm maps multiplication into addition. Thus, the logarithm function is a group isomorphism from positive real numbers under multiplication to the group of real numbers under addition, represented as a function. Logarithms can be defined to any positive base other than 1, not only e. However, logarithms in other bases differ only by a constant multiplier from the natural logarithm, and are usually defined in terms of the latter. For instance, the binary logarithm is the natural logarithm divided by lane, the natural logarithm of 2. Logarithms are useful for solving equations in which the unknown appears as the exponent of some other quantity. For example, logarithms are used to solve for the half-life, decay constant, or unknown time in exponential decay problems. They are important in many branches of mathematics and the sciences and are used in finance to solve problems involving compound interest. History. The concept of the natural logarithm was worked out by Grégoire de Saint Vincent and Alphonse Antonio de Sarasar before 1649. Their work involved quadrature of the hyperbola xy equals 1 by determination of the area of hyperbolic sectors. Their solution generated the requisite hyperbolic logarithm function having properties now associated with the natural logarithm. An early mention of the natural logarithm was by Nicolas Mercator in his work Logarithmotechnia published in 1668. Although the mathematics teacher John Spadel had already in 1619 compiled a table of what in fact were effectively natural logarithms. Notational conventions. The notations, lane x, and loge x, both refer unambiguously to the natural logarithm of x. Log x, without an explicit base, may also refer to the natural logarithm. This usage is common in mathematics and some scientific contexts as well as in many programming languages. In some other contexts, however, log x can be used to denote the common logarithm. Historically, the notations L and L were in use at least since the 1730s, and until at least the 1840s, then log or log, at least since the 1790s. Finally, in the 20th century, the notations log and lo are attested. Origin of the term natural logarithm. The graph of the natural logarithm function shown earlier on the right side of the page enables one to glean some of the basic characteristics that logarithms to any base have in common. Chief among them are, the logarithm of the number 1 is 0, and the logarithm as x approaches 0 from the right is negative infinity. What makes natural logarithms unique is to be found at the single point where all logarithms are zero, namely the logarithm of the number 1. At that specific point, the slope of the curve of the graph of the natural logarithm is also precisely 1. Logarithms to a higher base than e, such as those to the base 10, exhibit a slope at that point less than 1, while logarithms to a lower base than e, such as those to the base 2, exhibit a slope at that point greater than 1. While the methods for computing the value of e are fascinating from various mathematical perspectives, they all can be thought of as resulting from the pursuit of this condition. Another way of conceptualizing this is to realize that, for any numeric value close to the number 1, the natural logarithm can be computed by subtracting the number 1 from the numeric value. For example, the natural logarithm of 1.01 is 0.01 to an accuracy better than 5 parts per thousand. With similar accuracy, one can assert that the natural logarithm of 0.99 is minus 0.01. The accuracy of this concept increases as one approaches the number 1 ever more closely, and reaches completeness of accuracy precisely there, to the same extent that the number 1 itself is a number common to all systems of counting. So also the natural logarithm is independent of all systems of counting. In the English language, the term adopted to encapsulate this concept is the word natural. Initially, it might seem that since the common numbering system is base 10, this base would be more natural than base e. But mathematically, the number 10 is not particularly significant. Its use culturally, as the basis for many societies' numbering systems, likely arises from humans' typical number of fingers. Other cultures have based their counting systems on such choices as 5, 8, 12, 20, and 60. Loges of natural log because it automatically springs from, and appears so often in, mathematics. For example, consider the problem of differentiating a logarithmic function. If the base b equals e, then the derivative is simply 1, x, and at x equals 1 this derivative equals 1. Another sense in which the base e logarithm is the most natural is that it can be defined quite easily in terms of a simple integral or Taylor series, and this is not true of other logarithms. Further senses of this naturalness make no use of calculus. As an example, there are a number of simple series involving the natural logarithm. Pietro Mengoli and Nicholas Mercator called it logarithmus naturalize a few decades before Newton and Leibniz developed calculus. Definitions. Formally, lane may be defined as the area under the hyperbola 1x. This is the integral. This function is a logarithm because it satisfies the fundamental property of a logarithm. This can be demonstrated by splitting the integral that defines lane into two parts and then making the variable substitution x equals tar in the second part, as follows. In elementary terms, this is simply scaling by 1 a in the horizontal direction and by a in the vertical direction. Area does not change under this transformation, but the region between a and ab is reconfigured. Because the function a is equal to the function 1x, the resulting area is precisely lane. The number e is defined as the unique real number such that lane equals 1. Alternatively, if the exponential function has been defined first, say by using an infinite series, the natural logarithm may be defined as its inverse function, i.e., lane is that function such that exp equals x. Since the range of the exponential function on real arguments is all positive real numbers and since the exponential function is strictly increasing, this is well defined for all positive x. Properties. Derivative, Taylor series. The derivative of the natural logarithm is given by proof. This leads to the Taylor series for lane around 0, also known as the Mercator series logarithm of 1, that is the logarithm of infinity. Nowadays, more formally but perhaps less vividly, we prove that the harmonic series truncated at n is close to the logarithm of n. When n is large, at right is a picture of lane and some of its Taylor polynomials around 0. These approximations converge to the function only in the region -1 less than x1. Outside of this region, the higher degree Taylor polynomials are worse approximations for the function. Substituting x-1 for x, we obtain an alternative form for Lane itself, namely by using the Euler transform on the Mercator series. One obtains the following, which is valid for any x with absolute value greater than 1. This series is similar to OBBP-type formula. Also note that is its own inverse function, so to yield the natural logarithm of a certain number y, simply put in for x the natural logarithm in integration. The natural logarithm allows simple integration of functions of the form g equals f. An antiderivative of g is given by Lane. This is the case because of the chain rule in the following fact. In other words, and here is an example in the case of g equals tan, letting f equals cos and f equals sin, where c is an arbitrary constant of integration. The natural logarithm can be integrated using integration by parts. Let, then, numerical value. To calculate the numerical value of the natural logarithm of a number, the Taylor series expansion can be rewritten as: to obtain a better rate of convergence, the following identity can be used, provided that y equals, and r greater than 0. For Lane where x greater than 1, the closer the value of x is to 1, the faster the rate of convergence. The identities associated with the logarithm can be leveraged to exploit this. Such techniques were used before calculators, by referring to numerical tables and performing manipulations such as those above. Natural logarithm of 10. The natural logarithm of 10, which has the decimal expansion 2.302585509, plays a role, for example, in the computation of natural logarithms of numbers represented in scientific notation as a mantissa multiplied by a power of 10. This means that one can effectively calculate the logarithms of numbers with very large or very small magnitude using the logarithms of a relatively small set of decimals in the range. High precision to compute the natural logarithm with many digits of precision. The Taylor series approach is not efficient since the convergence is slow. If x is near 1, an alternative is to use Newton's method to invert the exponential function, whose series converges more quickly. For an optimal function, the iteration simplifies to which has cubic convergence to Lane. Another alternative for extremely high precision calculation is the formula where m denotes the arithmetic geometric mean of 1 and 4 per seconds, and with m chosen so that p bits of precision is attained. In fact, if this method is used, Newton inversion of the natural logarithm may conversely be used to calculate the exponential function efficiently. Based on a proposal by William Kahan and first implemented in the Hewlett-Packard HP41C calculator in 1979, some calculators, computer algebra systems and programming languages provide a special natural logarithm plus 1 function alternatively named ln1 plus x, lane, lnp1, lane1p or log1p to give more accurate results for values of x close to 0 compared to using lane directly. This function is implemented using a different internal algorithm to avoid an intermediate result near 1. Thereby allowing both the argument and the result to be near 0. Similar inverse functions named expm1, expm or exp1 meter exist as well. Computational complexity. The computational complexity of computing the natural logarithm is O lane n. Here n is the number of digits of precision at which the natural logarithm is to be evaluated and m is the computational complexity of multiplying two n-digit numbers. Continued fractions. While no simple continued fractions are available, several generalized continued fractions are, including these continued fractions, particularly the last, converge rapidly for values close to 1. However, the natural logarithms of much larger numbers can easily be computed by repeatedly adding those of smaller numbers, with similarly rapid convergence. For example, since 2 equals 1.253 times 1.024, the natural logarithm of 2 can be computed as. Furthermore, since 10 equals 1.2510 times 1.0243, even the natural logarithm of 10 similarly can be computed as. Complex logarithms. The exponential function can be extended to a function which gives a complex number as x for any arbitrary complex number x. Simply use the infinite series with x complex. This exponential function can be inverted to form a complex logarithm that exhibits most of the properties of the ordinary logarithm. There are two difficulties involved. No x has x equals 0, and it turns out that e2 pi I equals 1 equals e0. Since the multiplicative property still works for the complex exponential function, ez equals ez plus 2 pi k, for all complex z and integers k. So the logarithm cannot be defined for the whole complex plane, and even then it is multivalued. Any complex logarithm can be changed into an equivalent logarithm by adding any integer, multiple of 2 pi I at will. The complex logarithm can only be single-valued on the cut plane. For example, lane equals pi I 2 or 5 pi I 2 or minus 3 pi I 2, etc. And although I4 equals 1, for log can be defined as 2 pi I, or 10 pi I or minus 6 pi I, and so on. Plots of the natural logarithm function on the complex plane. Z equals re. Z equals im. Z equals lane. Superposition of the previous three graphs.